Okay, so get this worksheet. It's called the gradient and optimization. So this is the last part of, and I'm going to write down section 4.6. And then this is the last part of it. And it has some review of the previous section, which is relevant to what we need to do, as well as this last application problem on finding the absolute maximum and so on. Okay, the gradient and optimization. So here's a picture of f of x, y. Okay, and this is a nice picture. Maybe a little small, but here's the point, which is called p naught, y naught, 0, okay? And so that's the point. And the question is this: for a function which is z is equal to f of xy, the gradient at x naught, y naught is defined as, this is the notation for the gradient, evaluating at x naught and y naught, and this is f of x, f of y, right? That's simple. Evaluate at x naught, y naught. The gradient, in fact, let's go ahead and do this, okay? And what do you know about the gradient? Maybe I should write this in red. The gradient always points to the direction of the max or the greatest or the maximum rate of increase. Okay, so which, if you're standing at this point right here on the surface, which direction should I walk in order to maximum my rate of change, the steepness, the slope, right? And the answer, well, in this case, it looks like you should go this way, right? And that would be what the gradient looks like, my red arrow here. Remember, the gradient belongs to the domain, right? So you draw a gradient here on and a part of the domain, not on the surface itself. So you don't want to draw a gradient here, but just gradient down there, because the gradient is a two-dimensional vector. The length of the gradient is that maximum rate of change. Now notice here, if you reverse the direction, if you go the other way, let's say the maximum rate is 5, then the other way your rate will be -5, and that's going to be the minimum. Right? And it is perpendicular. The gradient is perpendicular to the level curve. Which level curve? The level, whatever the level curve is, that goes through the point x naught, y naught. Okay. So in this case, the level curve here is probably going to be something like this, and it is perpendicular to the gradient. All right. So you remember, this is, you know, what everything we learned in kindergarten, right? Depending on which kindergarten you went to. Okay, so now if u is a unit vector, you see this u here, that's a unit vector here. If u is a given unit vector in any direction, the directional derivative in the direction of u, and we denote this as d of f in the direction of u, okay, this just happens to be f dot u, right? The combination of f and u just doesn't look right. Sounds like it's a bad word or something, but okay, so f, you evaluate f at x naught, y naught, okay? And then you dot this vector, two-dimensional vector, with u, which is the unit vector in that direction, and just the dot product, as we saw before, the dot product is going to give you the rate of change in the direction of u, otherwise known as the directional derivative. All right, so this is all just a review of the previous section. All right, so now we go to maximum, minimum, saddle point. What do we say in our notes? Every local maximum, every local minimum, and every saddle point occurs at a critical point. So it is critical to find the critical points. And in fact, that's why it's called a critical point. A critical point can be found by setting fx and fy equals to 0, right? And use what to find local extremas? Oh, so it's a second derivative test. Okay, along with d, which is called the Hessian. Remember, it's, you know, d is fxx fyy minus fxy squared, right? So again, if the Hessian is negative, then it's a did I have that? No, you don't have this here. But if Hessian is negative, it's a saddle point. If the Hessian d is positive, then you look at the sign of fxx. If it's negative, then that's a local maximum. If it's positive, then it's a local minimum. All right. So, and they all happen at critical points. Okay, now for absolute extrema, you don't use that second derivative test because this is going to provide a local argument. So find what? Find all critical points. These are the usual suspects. And check all the boundary, okay? And then find the derivatives on those boundaries. Set them equal to 0 to find any critical points on the boundary. Check the boundary to find all candidates, the usual suspects for absolute maxima and minima, which we just did. And then compare the values at these points, okay? And of course, the highest of these values is the absolute maximum. The lowest is the absolute minimum. Do not use the second derivative test. You shouldn't care if you found the local maximum or minimum, right? After all, you may have a function that's like this, way up here, and you can find this local maximum, okay, by the second derivative test. But in light of the fact that you have a bunch of other points were much higher and much lower, you didn't eventually need to know this was a local maximum or local minimum or a saddle point, okay? So do not use the second derivative test if you're looking for global or absolute maximum or minimum. Okay, so let's finally do this application problem. This is a real application problem involving the ever famous or infamous postal service. Okay, so the postal service is international and the international regulations abound in the postal services. Here's one example, and I think this is still a real example. So you can't send huge packages through the postal service, okay? And so here's a rule, okay? We're trying to maximize the volume of a rectangular box or the content or the capacity of a rectangular box like this one under the postal regulation, which states that the length plus the girth cannot exceed 144 inches, right? So the girth means this plus this plus this plus this, okay? Assuming that, you have, this is a rectangular sort of a cross section. Length, of course, is that, okay? And so that's what we are looking for. Let's try to work this out. And so this is called an optimization problem with a constraint. All right, so we're trying to maximize something. What are we trying to maximize, by the way? Okay, well, let's try to figure out. And then maybe you can find the constraint and what to maximize here first, okay? Okay, since we have 3 dimensions here, let's just call the width x, and then the height y, and then the important length z. Okay, so you have x, y, and z, and the girth. What is girth here? That's sort of all the way around. The girth happens to be, in this case, 2x plus 2y, right? Because you have x here, y, and y. So it's basically the perimeter of this rectangle, and that's 2x plus 2y. Plus z, and this is exactly how the post office measures how big your box is and whether you can ship it or not. If it's too big, then you can't ship it. Different for UPS and FedEx and other places, but the International Postal Regulation dictates that the girth plus the length cannot exceed 144 inches. And so that means, of course, you want a maximum volume, right? So you won't have exactly 144. Anything less is not going to maximize it. So you want what? 2x plus 2y plus z, that's the girth plus the length, is equal to 144. It's usually less than or equal to, but we may as well just go for the maximum because we are trying to maximize the volume of it, okay? That's the constraint. And then the maximum, what we're trying to maximize is the volume. The volume V is X, Y, Z, okay? Now, the thing is, how do you reconcile this? Okay, so we use a standard procedure in mathematics, which is when you have too many variables, you try to replace one variable with the other ones. Okay, so by the way, this is a problem where in the optimization language, we say we are trying to optimize, we're trying to maximize X, Y, Z under the constraint that 2x plus 2y plus z is equal to 144. That's the language we use to describe this kind of an optimization problem with a constraint, sometimes with many constraints. Well, we have too many variables, x, y, and z. We'd like to make this into 2. And you can do that because this z, you can solve the constraint. Constraint is usually good to write one variable in terms of the other ones. It's 144 minus 2x minus 2y. Plug that in here. Your v that you're trying to differentiate, which is now can be written as a function of just x and y, right? That's the point. V as a function of x and y is equal to xy times z, right? And so I am going to write this maybe in different colors so I can clarify this. It's 144xy minus 2x square y minus 2xy square. I hope you can see that. This is the function I'm trying to maximize, okay? Now, also, it may be helpful if you know the domain. Is the domain all the points on the plane? Well, no, because you want x to be positive, y to be positive. Okay, y, by the way. Well, you can't have a negative dimension, right? That would be what the box sort of inside out or something that doesn't work. And also, you know, 2x plus 2y, okay, it has to be 144, right? So x can't be like 72. Okay, so I think you can say, now I don't know if it's important here, but x and y can't be 72 because if x is 72, that times 2 is 144, right? If x is 72, then y has to be 0, and that's not much of a box, right? So I think you can say this, right? We'll see that. Okay, you take the derivative of this, differentiate v, okay, to get the gradient. And the gradient, I think you can see this is, if you take the derivative of this with respect to x, you have 144y. And then this with respect to x, you get negative 4xy. And then this with respect to x is negative 2y squared. So this is your fx. Fy is similar. It's 144x minus 2x squared. That comes from this. And then from the last one, you get negative 2x. Negative 4xy is what you get from that side. Okay, so those are the fx and fy. Let's try to solve this. Fx is this thing. That's 0. That's what you want. Fy is this. This is a system of, again, non-linear equations. Okay. Now, yeah, I did say that x and y can't be greater than 72 because that would make the dimensions too big. Now, by the way, we don't include 0 or 72. So this is basically an open region like this. Actually, it's not even that because 72 times 72 doesn't work, okay? Don't worry about the domain at this point because for this, it turns out to be not so important. Okay, but you know that x and y have to be positive. All right, so how do you solve this system? That looks pretty hard, doesn't it? Okay, well, maybe I'll let you finish this. All right, yeah, go on and do this. All right, see you later. No, I can't do that. Okay, so let's go ahead and try to solve this. What techniques do I have in order to solve a system like this? Okay, well, here, let me just show you how you may go about doing this. Okay, divide. Now, you know that x and y are non-zero because if x or y are 0, then you don't have a box, right? So divide the first one by y. Notice here y appears in all of these, right? So it's 144 minus 4x minus 2y is equal to 0. You divide this by x and you get 144 minus 4y minus 2x is equal to 0. All right, so this gives us a new system. And in fact, I think this is a system of linear equations. 4x plus 2y is equal to 144. And the next one says 2x plus 4y is equal to 144. You can even make it simpler. Just divide everything by 2. 2x plus y is equal to 72. And x plus 2y is equal to 72. Let's call this equation 1 and this calls equation 2. Okay. Now again, you can solve this in different ways. I think what I will do is to multiply equation 1 by negative 2. Okay, so you get negative 4x minus 2y is equal to negative 144. That's equation 1 times negative 2. And the reason I do that is so now I can add these two equations together. Negative 3x, these will cancel, is equal to negative 72, right? So x is equal to 24. Okay, so you get, x is equal to 24. And so you can plug this into either equations. You can just plug it into y, and you say 2 times 24 plus y is equal to 72. So y is 72 minus 48, and that's also 24. So it looks like x and y are 24 inches each, and that would, by the way, give you z. Remember what z was? Z was 144. Let's go back and look at this. Z was 144 minus 2x minus 2y. So that's 144 minus 48 minus 48. And that's 144 minus 96. And this turns out to be 48. Okay, so here's the maximum volume. This is 24 by 24 by 48. Okay, and that is the maximum. Oh, by the way, how do you know it's maximum? Okay, and just in case, so just so you know, right? If you really look at this girth here, that's 2x plus 2y, right? This 2x plus 2y plus z has to be less than or equal to 144, right? And so, like I said, this is true, but x and y can't both be 72. In fact, x plus y cannot be bigger than 72. So the actual domain looks like this, excluding the boundaries, because the boundary points will just give you 0 box, right? And so you know that, so what I'm saying is along this side, and this side, all of these sides represent where the volume is 0, okay? And so if you found one place, it turns out this is 24, this is x, this is y, 24. This is an interior point, right? And so if this has is a critical point, you know that this has to be a maximum point because the minimum is 0, and so that's a maximum. Okay, but if you really want to show that this is it's a local maximum, you could, and you don't have to look for to show that this is a local maximum because we're talking about a global thing, right? So I should say along the boundary, the volume x times y times z is equal to 0. Okay, so you know, and all the other points it's positive because x times y times z has to be positive to represent the volume inside of this. And so this has to be a maximum point. But if you really want to check that it's a local maximum, you could do that, right? So what is the discriminant or the determinant, which is the fxx, you know, so fxx, that would be, where is my fx? This is my fx. Fxx is this my fx? Yeah, okay. Fxx turns out to be negative 4y. And fyy is negative 4x. And fxy is 144. Oh, that's a long one, isn't it? 140. Let's see. 144 minus 4x minus 4y. Okay, and so this is the same here, right? And so this will be like 16x, blah, blah, blah. Right? But you can try to finish this up, and then this will give you a positive thing. Okay, and because this is negative, you know, when you plug in 24, this will give you a local maximum. Right? But you don't really need to do this because, again, you know this has to be a maximum. I mean, the thing is, when you're looking for a box with positive volume, there has to be a maximum volume. When x or y or z is equal to 0, then you have the minimum volume of 0. So whatever you found is the maximum. Anyway, so this is how you apply, you know, the techniques we learn in optimization problems. Okay, I think that's it for section 7. We have a very sort of a brief section, section 8, which is another method of optimization, which some of you may actually like, and you may even want to play with it. It's called Lagrange's method, and so that's section 8. And so hopefully this is almost the end of chapter 4 for you. Okay, so as I said, 4.7 is a long section and you will spend a lot of time doing your homework. But again, every minute you spend is worth it, okay? My background here, you see this point, the origin turns out to be point, I don't know if you can see this, but right here, you can see this point, which is a saddle point, and that would be a critical point you can find by letting f of x and f sub y equal to 0. All right, so have fun doing your homework. I know that that's the time. I know you may not like or enjoy doing homework, but that's like your weightlifting. That's when you build your muscle. It has to be constructive and cause a little pain, right? And it is time consuming. But remember, without spending time, you really can't get to know anyone or anything. And so that's why I'm encouraging you to do all your homework problems. Even though it may take time, that's the time commitment that you need in order to successfully learn calculus. Notice I didn't say successfully pass calculus, because you can maybe successfully pass calculus without actually learning much of it. But I do want you to learn and gain the knowledge and appreciate that beauty of what we call calculus. All right, so I will see you in section 4.8. Until then, have a great day. See you later.